You know, as a medical diagnostic tool, we're all familiar with the CT scanning, but from a manufacturing standpoint, it's also useful technology for looking at fine detail and characterizing the internal structure of components in a non-destructive way. I'm with Jesse Garrett, he's president of Jesse Garrett Metrology Center. Jesse, I understand that you use CT technology in a different way, a more powerful way, to actually look inside things like castings, forgings, and complex structures.
Exactly, Jim. So CAT scan technology for industrial applications allows us to see inside primarily for clients from a reactive point for failure investigation. However, some of our more proactive clients are using CT inspection for pre-production validation and production validation. And what I mean by that is they're looking for internal flaws such as fit and function, dimensional changes, first article inspection, which allows clients to get into production a lot more faster than traditional means.
Now, Jesse, an obvious example I think of is aerospace. There's a very famous Iowa City DC-10 crash caused by an inclusion in a blisk, which made it through the quality program as it was 15 or 20 years ago. And there's really no way to see that with any surface inspection. Zyglo, Magnaflux will not find an internal flaw like that. But it's safety critical at the same time. Is that the kind of application we're looking at here?
Yes, so clients would be looking for failure investigation on some of those parts from a crash that you'd be looking to do some diagnostic on. With CT, we're going to very high precision compared to a medical application where it'd be a lower resolution. Industrial applications allow us to get down to the micron value. So that allows us to see separations in between components and fit and function where it'd be very difficult without traditional means.
Would you use this technology as a quality monitoring technology in process? Would you use it to verify a finished product?
CT is a very costly in-process system to set up, along with it's a very difficult technology to adopt into a manufacturing line. So a lot of manufacturers, unless you're manufacturing a very high volume number of parts, my company as a service company, we handle the smaller volumes and the limited run parts, where clients can't justify the cost of either putting a standalone system or a production CT system in their own facility, but still have that need for that high-end service.
Now, and many pundits claim the future is metal additive manufacturing for metal parts. And of course, additive manufacturing, 3D printing, allows you to create complex internal structure in an enclosed component. So once it's built, there's really no way to know exactly what you have on the inside. Is that a potential application?
Actually, additive manufacturing is a huge application for CT, but it was limited due to the technology in the past. So microfocus CT allowed us to see internally very quickly within approximately about a 1 hour scan time frame. That allows clients, especially in the additive manufacturing side, to see internal components, porosity, residual powders within those parts, which are key to putting those parts into production. Higher energy CT for accelerator based was a very slow and a very difficult process to use CT for additive parts. It would take almost a half a day for scanning. It was very poor resolution, and it wasn't really a feasible technology when the inspection process is approximately 1/3 the cost of the part itself.
Now that's a significant cost of the part itself, so I see that you're looking at safety critical things or things where failure is simply unacceptable. Nuclear industry perhaps?
Not so much nuclear. We do a lot of oil and gas, aerospace, space, defense applications for those technologies.
We've been talking about things we associate with metals, metallic parts. Is other materials possible? Resins, ceramics?
Yes, so resins, ceramics, a lot of composite weave, carbon fiber weave for inspection. We get into circuit board inspections for parts, epoxy overmolded applications as well. We get into lower density alloys, aluminums, titaniums, very great application for CT. Once you start to get over the super alloy threshold and getting into your tungstens, your leads, your golds, it becomes a technology that it requires so much power to shoot through the part, we lose a lot of resolution then too. So it's kind of a trade-off and not particularly applicable for a lot of those higher energy alloys.
So those are shielding materials to start with. How much power are we talking about here? Because you're talking about enough energy that you can penetrate some fairly heavy walls, metal castings.
Yes, well it all depends particularly on the CT system that's being used. At our lab we utilize 9 CT systems because not every part matches up differently with CT system. When you look at the medical application you're talking about, most people are actually set up the same. We have a head, we have a body, but when you look at parts, everything is different. So that's why not one system matches up properly. For energy-wise, we look at running from 80 kV systems all the way up to our higher energy systems, which is 3 MeV. So 3 MeV allows for approximately 20 inches of iron casting, and we get into aluminum casting applications. We're shooting through about 39 to 40 inches of aluminum.
Jesse Guerin says consider CT scanning as a accurate, repeatable, non-destructive testing methodology.